Alrighty, so let's jump into it. I'm going to start by sharing my screen. Perfect. So a 9-kilogram block is resting on a ramp inclined at 30 degrees above the horizontal. What is the magnitude of the normal force? First thing I'm going to do is draw our scenario. So we have this incline, which is at some angle degree theta, and we have our block on it, which has some mass m. These numbers are over here, but for this purpose of this math, we're not going to worry about it. All right, so the first thing we want to do is draw our free body diagram, or FBD, which is analyzing the forces acting on this block. The most obvious one to always remember is weight. So we know that we have weight, which always points in the downward direction. We have a normal force, which points perpendicular to our surface. And we have a force of friction, which points contrary to where motion would be. Let's label this friction, and we'll label this the normal force, N. All right. And so what I'm going to do is actually a little trick here. I'm going to define my x and y axes as follows. I'm going to make x point along the ramp up like that. I'm going to make y point normal to the ramp. So the force of friction points along the x-axis, and the normal force points perpendicular to the ramp. All right, so that means that the only thing I'm going to decompose along my axes is the weight. So how am I going to do that? Well, if I were to draw this diagram over here, where this is the ramp and this is the direction of the weight, and we know that this angle is theta, with some clever geometry, I can say confidently, and so this way would be decomposed along this force and decomposed over here. So that means since I decomposed it along this line, I know this angle is 90 degrees. I know that this angle is theta. We know from before that this angle is 90 degrees. So this angle over here is 90 minus theta, which means that this angle over here is equal to theta as well. So back to our original FBD, if I were to decompose force, which I'll do that in green, along this axis and along this axis, then I know that over here is angle theta, which I just proved over here. All right, so now we jump into it with Newton's laws. Newton's, I think, second law that says that force equal to mass times acceleration. Nothing's accelerating, so the sum of the forces in total is equal to 0. Which means the sum of the forces in the x direction is equal to 0, and the sum of the forces in the y direction is equal to 0. The normal force points along in the y direction, so we're only going to worry about that one for now. So what forces are in the y direction? We have the normal force, which points to the upwards, which is a positive direction, plus the weight, which points, it's actually a component of the weight. Which component points along the y direction is this component over here, which is the weight times the cosine of theta. And we know that this is going to sum to 0. All right, so now if we take into account our directions, like I said, the normal force, the magnitude of the normal force is a positive direction. Meanwhile, the weight is negative. So now I'm just going to make it negative. All right, so now with a little bit of algebra, we can say that that's cosine theta is equal to W cosine theta. Normal force is equal to mass times gravity, which is the cosine, which is what weight is, times the cosine of theta. And now what we'll do is plug in numbers. The normal force in magnitude is going to be equal to 9 kilograms times 9.8 meters per second squared times the cosine of 30. If you plug that all into your calculator, you are going to get the answer. I don't have a calculator right now, so I'm going to leave that math up to you. Right,